Hi there, and welcome to Bringing STEM to Light, Module number 5, presentation number 2. In this presentation, we're going to take a look at refraction. And refraction is the bending of light. And mostly, we observe the bending of light when we see a rainbow or when we see something through the water that appears to be somewhere where we know it's not, or when we look through a lens and some magnification has happened, and refraction is also at work in many telescopes and also in microscopes. So refraction is yet another example of how all we see is light. So what's going on with this duck here? We know that that duck is not split in half, right? We know that the duck's feet are in fact connected to its body, the same body that we see above the water. It's not shifted over like that. But what happens is as light passes from the air into the water, it bends. And it bends and then it reflects back to our eyes. And because it bends, it changes location. And so even though that duck is all together, it appears as though it has been split in half, because all we can see, we can't really see the duck, can we? Now all we can see is the light that has been reflected off of it through the water, and it has caused it to appear as though it is in a different place. When you look through a lens, it doesn't actually change the size of the print or change the size of what you looked at. It bends the light in such a way that it appears as though that the thing that you're looking at has changed size. And over there with the rainbow, what's happening there is as sunlight passes through little tiny droplets of water, they pass from the air into the water and then back out into the air. And each time that light passes from one medium, like air, into another medium, like water, it bends. And it just so happens that in a rainbow, each of the wavelengths of that sunlight bend at a slightly different angle, and so it spreads it out, very much like in the earlier lesson when we were looking at color, like a diffraction grating could spread out a spectrum of light, could actually separate out the various wavelengths and colors of light. Now, refraction is due to bending of light as it passes through something, and diffraction, which is what we observed with the little diffraction grating, is the bending of light as it passes around a very, very small barrier. So they seem very similar, but they're actually quite different. So let's look at this bending of light a little bit more closely. So when light passes from one medium into the other, here we have a beam of light going into, it's either a glass or an acrylic block. For this conversation, it doesn't really matter which. What matters is that the block that it's passing through is more dense than the air that the incident ray is coming from. So as soon as it hits that block, that light is going to slow down, and the slowing down is going to cause it to bend. And when it bends, you can see that it has moved, right? Now, when you put all the rays together and you have bending light, what you get is an image that has actually shifted. Here, we're just looking at one ray of light, and so you can see that that ray of light has shifted. But if you take that idea a little further, that's why we see things as misplaced, or we'll call it misplaced. We see it where it doesn't actually exist when we look into the water. Now, notice also that that ray of light bends yet again. It doesn't come out of the block at the same angle that it's traveling inside the block, and that's because the density is changing again, right? It's leaving a more dense medium, and it is leaving into a less dense medium. And if you pay close attention, you'll notice that as it goes from less dense to more dense, it bends towards the middle, or the normal, and as it goes from more dense to less dense, it bends in the other direction. It bends away from the normal, and that's how refraction works. So let's take a look at this speed thing just a little more. Why in the world would changing speed cause the light wave to bend? Well, here's an analogy that describes it pretty well. If you were to imagine, instead of a light wave, a line of soldiers who are marching along the sand at the beach, and they are marching towards this barrier, right? This barrier that is the distinction between the sand and the ocean. And as they cross from the sand into the ocean, they're going to have to slow down, right? Because that ocean is going to cause them to not be able to march as quickly. And as they slow down, that the angle begins to change. And if you were to line students up and have them do this exercise, they would in fact have a kinesthetic experience of being able to be that beam of light and have the experience of as you begin to move more slowly, there's kind of some drag, and it takes some time for those other soldiers to catch up. And then as they leave, the same thing happens, right? They speed up as they leave the water and come out onto the sand, and they do that at different rates because they're not all coming into or out of the water at the same time because they're hitting it at an angle. And so we're not really talking about soldiers, we're talking about waves of light, but the analogy is actually a really, really good one. And if you really want to make the analogy reflect what's really happening, you have to kind of ask yourself the question, how is the slowing down happening? Are the soldiers shortening their pace? Are they taking smaller steps? Or are they taking steps at a slower rate, like same length of stride, but more slowly? And that is the analogy for what's really going on with the light waves, right? Because light waves have a kind of a stride, and we'll call that the wavelength, and they also have a pace, and we're calling that the frequency. Remember way back in the beginning when we were talking about the wavelength and the frequency of the waves of light? Well, here's one place where it matters besides color. So, one or either of those things would actually slow things down, right? You can do it yourself. You can march, and you can slow down the frequency of your steps, and that'll get you there more slowly. Or you can shorten your stride, and that'll get you more slowly. Or you could do both. But what's happening with light is that the frequency of the wave does not change. They are marching at the same rhythm, but they're taking smaller and smaller steps. So the wavelength gets shorter and the frequency stays the same. And that is what's happening with refraction. Light travels from a less dense medium into a more dense medium, and the stride or the length of the wave gets just a little bit shorter, and that causes that bending that we saw with the line of marchers going towards the ocean. And now we'll stop and take a look at how to use the goodies in your kit or the things that you've gathered for using in your classroom to observe refraction. And we'll also start looking at what happens when light passes through lenses, because that's the basis for a whole lot of technology. Cameras and telescopes and microscopes and eyeglasses, all kinds of things. So let's take a look at what happens when we watch refraction with a beam of light through a lens.
The first thing you're going to want to do is take out all three of your light blocks and get your set of lenses. And if you remember, we started with one is a trapezoid, one is a double concave lens, and then we also have a double convex lens. And we're going to start with just one light blocks and your trapezoid. You're going to orient the light blocks on the table so that you can see the line of light shining forward. And then you're going to place your trapezoid with the smoky side down on the table flat, and point your light at your trapezoid at an angle so that it's not going straight on. If it's going straight on, you won't be able to see refraction. But if you move it so that the light is coming in at an angle, you'll see that the light comes in as a straight line, and then that straight line appears to kind of bend or even almost break and jump over, and it's passing through the acrylic at a different angle, and then when it leaves the acrylic, it goes back to the original angle that it was coming in at. And that's refraction. The next thing we want to look at with refraction is different shapes of lenses causes light to bend in different directions. And that is actually the basis of how a lot of technology works. Think of a microscope or a camera or even just your eyeglasses. Those lenses cause the light to bend in different ways and allow us to see different things. So let's see what happens when you use your double convex lens. This is a lot like the lens that's in your eye. If you line your light blocks up so that you see 3 parallel lines all very close together as you can get them, and you place your convex lens right in the middle, what you'll see is that the light there bends towards the middle, and it all comes together at one point called the focal point. And that is how your eye works. That focal point is your retina, and that's where the image is formed. But what happens when you use a different shape lens? So now we're going to use our double concave lens, and again put the frosted side down and place it in the path of all 3 beams, and you can see that the light spreads instead of comes together at a point. And what happens if you use both lenses? So start with your double convex lens again. Position it so that you have a distinct point. And now imagine that this is the lens in your eye, and that point is the retina. But when you have a vision problem, that light isn't focusing directly on the retina. It's misplaced. So we can add another lens to move that focal point. So place your double concave lens directly in front of it, and you can see that it has moved your focal point further away from the lens. And that is the basis of how all lens systems work, whether it's for a camera, a microscope, a telescope, or a set of glasses.
So there you have refraction through lenses. A convex lens, which is curved outwards on both sides, or even just on one side, is going to bend light inwards and create a focal point. And a concave lens is a diverging lens, and that's going to spread light out. And lens systems are built by adding lenses to each other and putting them together. Like when you put another lens in front of your eyes, you use the eyeglasses to change that focal point so that it lands directly on your retina. If you look at the elaborate activity for this section for refraction, there is a great lesson on using gelatin to create lenses to solve a vision problem. And that is a great way for kids to take what they've learned and see if they can apply it to a problem that a lot of them are really familiar with.